Okay, all right. So can you see the screen?
Good evening, sir. Yes, sir. Yes.
Okay. So let us begin today's session. So this is live tutorial session number 9. And in this today's session, we are going to discuss about the Peltier cooling. So as usual, we will first we will first revise all the contents for week 9 and then we will solve the problem. So what is Peltier device? The Peltier device is also a semiconductor material junction, and this Peltier is used as a heat pump where it transfers heat from a cold body to a hot body from lower temperature to higher temperature by providing electrical energy at its terminals. So as we all know that this heat transfer from a means in natural way the heat transfer from a hot side to cold side. But if you want to transfer the heat from a cold side to hot side, then you have to do something that you have to provide some external energy so that the heat from the cold body transfers to hot body. The work done by this Peltier device is that only. And the application for this Peltier device is like refrigeration, cooling, generating heat, etc. So how does this Peltier effect comes? So this scientist, French watchmaker and physicist Jean Charles Peltier are the main scientists who have discovered this effect. So here two metal having two metal junctions and copper and nickel. And if you see here, this current flow through this junction of dissimilar metal establishes temperature difference. And this direction of current flow that decides that whether junction is cold or hot. And how you write this heat absorbed or generated, that is directly proportional to current I. And if you write this equation, then it comes out as Q equal to pi I, where this pi is Peltier coefficient. Now coming to this nowadays, so in today's this Peltier element is solid device that is made of semiconductor material. So this is series connection of P and N type semiconductors, and this is the industry based Peltier device. You can see here. So this is the QC amount of energy extracted from the cold junctions, and for this Peltier device, we are giving electrical energy that provided to this Peltier device, so that it extract the energy from the cold junction. Therefore, this QS will comes out QC plus electrical energy. So this QC is the energy extracted from the cold body, and that you can also tell it as heat flow. So this heat flow you can write it as rate of energy flow. So this is the rate of something. So you can write it as also power. So it is joule per second. So that's why the unit of this energy extraction from the cold body, or whatever the Q denoted here, it as watt. And this coefficient of performance is very important term, and this coefficient of performance is the ratio of energy extracted from the cold junction to this electrical energy need be provided to this Peltier element for pumping the heat energy. So higher the COP, so higher COP is desired. It means that we are extracting more amount of energy from the cold junction while providing the less electrical energy. So For this ideal Peltier device, the electrical energy needed to pump is 0, and that provides COP, coefficient of performance, as infinite. So this higher COP means removing large amount of heat with least electrical energy input. So that is the desired one. Higher COP is desired one. Now coming to this data sheet of this Peltier element, Peltier device. So this is layered technology, and various features for this Peltier device and applications are given. And this performance specification for this Peltier device is very important one. So here this, I think someone mic is turned on. So please turn it off. Mohan Chindambram, I think your mic is on. Okay, thank you. So the data sheet of Peltier device is very important. Based on your application, you have to choose what type of Peltier element have to select. And for selection of Peltier device, you have to see the data sheet, like if you are what amount of energy you want to extract from the cold body, and what is its voltage and current rating, maximum voltage and current rating based on the application. So if this the amount of energy extracted from the cold body is increased from this Q max that is given data sheet specification, then this internal resistance of Peltier element RP present inside this device increases, and that means I square RP loss also increase. So this will reduce the amount of heat far from the cold body to hot body, and this temperature coefficient between hot and cold junction will fall. So you have to take care this Q, the amount of heat extracted from a cold body to hot body should be less than this Q max. And for 25 degrees Celsius, this hot here for two different temperature ranges given. That is one for 25 degrees Celsius and another one is for 50 degrees Celsius. So you have to take care that the amount of energy, hot heat energy that you want to extract from the cold body should be less than this Q max. Now coming to this thermal and electrical characteristics for this Peltier element. So this graph shows for different current flow through this Peltier element, and this thermal graph is for delta T, QC versus delta T, and for electrical this is voltage versus delta T. So from this graph, what you can conclude for the thermal, first we will see for the electrical, as this delta T increases, this you can see if you go this side, this delta T increases, and for a certain current value, for constant current value, like here 3.0, cross denotes 3.0, circular one denotes 6.0, this triangular one denotes 9.0, and this how you can say, and this square denotes for 3 sorry, this cross denotes 0.6 ampere, this circular one denotes 1.2 ampere, this triangular denotes 1.9 ampere, and this diamond shape denotes 2.5 ampere, and this square shape denotes 3.0 ampere. So if you see this as delta T increases, this voltage across Peltier cooler also decreases under the given condition for constant current. So these lines denotes different current values. And for this thermal effect, as the delta T increases, removal of heat from cold side decreases under the given condition of constant current. Now coming to the application of this Peltier device. Now if you want to install this Peltier device in some applications, then how you have to use it. So suppose you want to extract extract heat from a certain body, certain element, then you have to fix this Peltier device in between the means between outer atmosphere and this device. So here we have taken, like any other thing also you can take out in the place of atmosphere. So if you extract the heat from hot to cold with this help of heat pump, with the help of heat pump, and that heat pump is the work of heat pump is done by this Peltier device. So again, this natural tendency of heat flow is from this hot side to cold side. So if you extract the heat from cold to hot side, so again this heat from hot to cold side will come naturally. So we have to make sure that this heat from hot junction is removed. Otherwise, the system won't work effectively. So this is very important. I means whenever you are installing this Peltier device, you have to make sure that this whatever the energy you have extracted from the cold body, it should be removed from the hot junction, or it should have been dissipated. Otherwise, the system would won't work effectively. So these are for some mathematical how you can make the circuit for the thermal effects. So here the thermal resistance is the ratio of delta T upon the amount of energy extracted from the body. So this thermal resistance unit is per degree Celsius or per degree Kelvin per watt, degree Celsius per watt or degree Kelvin per watt. And if you make this circuit for this thermal effect, then you can make it like this QC, the amount of extracted from the cold body, and then we are having this thermal resistance, and for this uh, this is the temperature at junction J, so Tj, and this ambient temperature denoted by Ta. So this temperature both have denoted as this node. If you write the equation for this thermal visualization, then you can write Tj minus Ta equal to R thermal resistance into the amount of energy extracted. So suppose here if your ambient temperature 40 degrees Celsius and this thermal resistance given as 10 degrees Celsius per watt, and this amount of heat you want to extract it from the body, that is given as 20 watt, then this junction temperature will come as 240 degrees Celsius. So here if you see this expression, we can see that we don't have control over QC. That means how we don't have control over QC, because based on your design, based on upon your application, you have made some circuit, you have made some device, and based upon the power extracted or based upon the current flow, this Q will be generated. This Q seed will come in your circuit. So you have to maintain the temperature of the your something you have made or something you have designed within a limit. Otherwise, this the element or something device you have made that will not work properly. So this is very important. So you have the amount of heat generated by it is not in your hand, because you have made your circuit, but the on the base of application, on the base of this amount of current flow, that will decide this the heat generated from the device. And we don't also have control over this ambient temperature Ta. Only thing we are in our control is this thermal resistance, that is R theta. So if you control over this thermal resistance, then you have then you can uh, then you can control then you can how you can say then you can control over this heat present at this heat energy that is available at this case or available at the junction. So how can we reduce this thermal resistance? That is question. So such that this if you reduce the thermal resistance, more amount of heat energy will you are able to extract from the body. So that is the main thing. The problem statement is that how we can reduce the thermal resistance such that more amount of heat energy you can extract from the case or from the body. So here this two thermal resistances have been denoted, one from junction to case and from the case to ambient, and both you can take it as 0.5 degree Celsius per watt and 9.5 degree Celsius per watt. So this junction to case you cannot control, but this case to ambient you can reduce this. And how you can reduce? With the help of heat sink or with the help of this Peltier plus heat sink. So let us try first with the heat sink. So if you have used this heat sink over this element, then and then you can write, you can make this thermal visualization of this circuit. So this R theta JC will come, that is the thermal resistance between junction and case, and then thermal resistance between case and sink will be denoted as R theta CS, and from the sink to ambient we have denoted thermal resistance as R theta SA. So based on the design of this heat sink, you can reduce this thermal resistance. So now if you want to write this expression for the circuit, then it will comes at Tj minus Ta, junction temperature minus Ta, and this R theta Jc into Qc, the amount of energy extracted. So you can treat this Qc as equivalent current that we use in electrical circuit, and this R theta Jc as resistance, and this T temperature as voltage. So if you see this R theta Jc is 0.5 degrees Celsius per watt and Qc is 20 watt, then this will come as, then this will come as 40 degrees Celsius, and R theta Cs is 0.1 degrees Celsius per watt and Qc is 20 watt, then it will come as 0.1. So 2 degrees Celsius. This is 10 degrees Celsius. And then this will come as 20 degrees Celsius. So if ambient temperature is given as 40 degrees Celsius, so this will come as 40 plus 10 plus 2 plus 20, that will come as 72 degrees Celsius. So you can also write Ts, Tc and Tj. So this Ts will come as 60 degree, and this Tc will come as 62 degree, and this Tj will come as 72 degrees Celsius. So you can play with this thermal circuit like this. Now coming to next part. Now we have this Peltier element with the along with this heat sink. So before installing your Peltier element, you have to just specify whether this Peltier element is within the according to the data, according to your requirement. Means whatever the amount of extracted from the body from this element, that should be less than this Qmax that provided in data sheet, and this current IP is being provided to this Peltier element should be less than this Imax that also comes from the data sheet, and delta T that we know from this hot body to cold body difference, that is also within the specification according data sheet. So now this heat given to heat sink means like you have used this filter element and this heat sink. So the heat that is provided to the heat sink should be removed as well. Otherwise, whatever the temperature at the heat sink will increase. And since delta T constant for particle value of this Peltier current, so this P case will increase, this case temperature will increase, and eventually this junction temperature will increase. That means whatever the element or body in which you want to extract the heat energy, this temperature of junction will increase. So this heat removed from the Peltier element from cold side should also be given to this ambient by heat sink at the same rate, then only this whole system will work properly. So sometimes this heat sink size is reduced and a blower fan is added instead. So what is the solution for this problem? If you don't remove the heat from the heat sink, then it again flow back to this case or to the junction. Then again, whatever the energy you have put to extract the heat energy from the cold body to hot body, it again come back to your case or your junction. So in order to in order to do it properly, you have to either reduce the heat sink size, you have to reduce the heat sink size and use the blower fan. You can increase the heat sink size, but the problem is that by increasing the heat sink, you can also extract the more heat energy from the case or body. But the problem is that uh, it will in just degrade the quality of design of your product. So it's better to just reduce the heat sink size and use a blower fan along with the heat sink. So this we have used this peltier element, and then we are having this heat sink and then the fan. So this heat removal from the hot junction of Peltier element is not done properly, then the whole system will not work properly. So that's why we have installed this heat fan along with this heat sink. Now coming to the next part, this thermal aspects. So heat flow is affected by four mechanisms: conduction, convection, radiation, and mass transport. So we will see little bit about all of them, and the combination of all of the above is used at heat removal from the hot surface of the Peltier element. So this all mechanism we will see briefly, and we will solve some problems based on that. So before that, we are having some relationship, thermal relationship. First one is that we have seen about this thermal resistance, R theta thermal resistance. So it is Q equal to the energy extracted, heat energy extracted from the cold body equal to this delta T upon R theta. And if you write in this thermal resistivity form, then you denote small q equal to this heat energy upon per unit area. So this small q denotes this heat energy extracted per unit area. Therefore, this R theta we call it a thermal resistivity, and R theta will come as A into this thermal resistance. Now, how you can write in thermal coefficient form? Then you can write a small q equal to h into delta T, where h is the reciprocal of a small r theta. Now, first let us see this heat transfer by conduction. So here we are having an element having a area of A. So the per unit amount of heat extracted from the body is denoted by a small q, that is q upon area. So this Q we denote as H into delta T. So this K we write H into delta X. So what is K here? Can anyone tell? So H is thermal coefficient and thermal conductivity be defined as multiplied with thermal coefficient to delta X, and delta X is the thickness of the block. So delta X is thickness of block along with this heat flow happens. Along the heat flow direction, and this K is thermal conductivity. So there are some terms you have to keep in mind. So thermal conductivity is multiplication of thermal coefficient with the thickness of block. So this unit will come as watt per degree Kelvin per meter. Therefore, this thermal coefficient will also write in terms of thermal conductivity and thickness of block, and then we can write this heat transfer by conduction per unit area will be K into delta T into X. If you multiply with the area, then it will come out as this one. So you have seen this thermal resistance form. So we know the thermal resistance form is P equal to delta T upon R theta. So R theta will come from here, this thermal resistance in when we see this conduction form. So greater this cross sectional area, a smaller will be thermal resistance. So if this area will be more, this thermal resistance will be less, and better will be the heat conduction through the material. So this is the reason for we having convoluted fins in the heat sink. So if you see heat sink, then it is in the shape of this one, such that this area will increase. So these terms are very important. We will see some problems also. And now we see the thermal conductivity for some metal or some medium. Then for silver, it is having higher value 410. And then for copper 385, for aluminum 211, for steel it is 47.6, for glass it is 1.05, for thermocol it is 0.025, and for steel it is 0.026. So these are good insulation, good thermal insulators. Those values are very less. So for glass it is very less value. For thermocol it is very less value. For steel it is less value. So these are not good transfer of heat. And apart from this, silver, copper, aluminum, steel, they are good transfer of heat energy. So if you see the heat sink, these are also made from, I think, aluminum. That is good transfer of heat. Now coming to this next part, that is heat transfer by convection. So as we all know that this for convection, heat flow occurs between a solid and a fluid. So we are having this surface, and here we are having the medium, either fluid, that is air or liquid. So hot air is less dense, so it moves upwards, and cool air is dense, so it moves downwards. So this is natural circulation of fluid, that is called free convection. And if a fan is kept externally to remove heat, then it is called as forced convection. What is free convection? Free convection is that this hot air automatically goes upwards while this cool air automatically goes downwards. So this is free convection. While this, if you use the fan to speed up this process, then that is called forced convection. Now, if you write the term for this convection, then we are before the conduction, we have seen for conduction, that is Q equal to K into A delta T upon delta X. Then multiplying and dividing by X, that is characteristic dimension, upon the numerator and denominator, then it comes like that, comes like this. So here we define a number, that is Nusselt's number. Nusselt number is X upon delta X. So X is characteristic dimension. So this is for heat transfer. Heat transfer rate for this convection, K into A into Nusselt number into delta T upon X. And if you write for thermal assistant convection, then again you have to compare with the conventional form. We know this conventional form is Q equal to heat energy extraction is Q equal to delta T upon R theta. So comparing with this actual expression, then you will get thermal resistant convection as X upon K into A into Nusselt number. And for this conduction, we got delta X upon Ka. Now, Nusselt number determination is one of the important aspects. So these are this empirical relationship, how you will find this for free convention and forced convection. For free convention, this first we'll find this Rayleigh number, and for this forced convention, we will find this Reynolds number. And Reynolds number expression is this one, U into X upon mu, and U is this mean velocity, and X is the characteristic dimension. And where this for free convention, this G is the gravitational coefficient 9.81 meter per second, and beta is the coefficient of thermal expansion of fluid air, that is 1 upon 330, and X is the characteristic dimension. Delta is this thermal diffusivity of fluid air, 2.6 in 10 to the power minus 5 meter square per second, while this mu is kinetic viscosity air, 1.8 into 10 to the power minus 5 meter square per second. So kinetic viscosity of air is 1.8 into 10 to the power minus 5 meter square per second. So this mu is kinematic viscosity of air. Now these are for some standards. For some standards interface for some standard solids, like for horizontal flat plate and vertical flat plate, how you can find this characteristic impedance, and based on this Rayleigh number, that will decide the laminar flow or turbulent flow. So for laminar flow, Rayleigh number is belongs to 10 to the power 2 up 10 to the power 2 to 10 to the power 5, and for turbulent flow, this Rayleigh numbers is about 10 to the power 5. Then these Nusselt numbers will also change, and for vertical plate, you can see this correct characteristics dimension X, and characteristic dimension for this circular vertical flat plate, and again for laminar flow and turbulent flow, you can see this expression. Now for horizontal cylindrical solid, these are the expression for Nusselt number characteristics dimension for laminar flow and terminal flow, both the Nusselt numbers given. For vertical cylindrical solid also, this Nusselt number expression is given, and for parallel flat plate, this Nusselt number expression is given. Now this, coming to this example, we have taken example for this representing a volume of wax packed inside thermocol gray, and here first we'll see with aluminum block reconvention problem. So you can go through it. So this will, if you solve this, then you will get heat flow to ambient will be, this amount of heat extracted will be coming as 24.39 watt. And now with forced cool system, if you see, then the amount of heat flow to ambient will come as 66.07 watt. And if you see this compared with this free convection, then you can see that it is coming as 44.4 watt and here 66.07 watt. So this has significantly increased compared to without fan case, that is free convection. Now coming to the next part, that is heat transfer by radiation. So this radiation, we have seen conduction, and then we have seen convection, that is transfer of heat through fluid, and then we are going to see this radiation. So radiation is the transfer mechanism from the hot body through electromagnetic waves. So it does not require medium. Whatever the energy we get from the sun, that is coming from the radiation. So with from there you can visualize the concept of radiation. So it does not require a medium for transferring heat. And if you see the expression for radiation, that is Q equal to HR into A into delta T, where A is the area of surface perpendicular to radiation direction, while HR is the radiation thermal coefficient. And HR can be written as 4 into sigma into epsilon into 1 minus phi into T of T1 plus T2 upon 2 upon to the power Q, where sigma is the Boltzmann constant. Its value is 5.67 into 10 to the power minus 8, where epsilon is emittance, and the emittance value for different metals for different surfaces is given. For anodized aluminum black, that is given as 0.8, and for polished aluminum it is given 0.0095, and for rough surface aluminum it is given as 0.18. For tungsten it is given as 0.33. For polished copper it is given as 0.007, and for wood it is given as 0.9. And the shielding factor is given will be given the problem if they provided the some problems where these two surfaces are given, and if there is single or parallel system, then we have to take the shielding factor as 0. Now coming to the last part, that is heat transfer by mass transport. So the movement of fluid mass is used for transferring heat from one place to another, and we can see one example in refrigerators where this freon fluid is used for transferring heat from chamber to evaporator, and then gets exchanged to the ambient through this radiator. And you can see one example in car engine also, where this concept is used to cool down the car engines. I think you have seen in the refrigerators, in the back side there is this type of shape. So that shape is required for transferring the heat from chamber to from the refrigerator from the refrigerator machine. And if you see the expression for heat transfer mass transport, here we are using this mass flow rate dm by upon dt, and Cp is a specific heat of fluid, and delta T is the difference between hot side and cold side. Therefore, you can write this r theta m for mass transport, that is 1 upon dm upon dt into Cp. Again, you can compare with this conventional one, q equal to delta t upon r theta. So if we compare this one to this, you will get r theta m. So on comparing, you will get equivalent resistance in mass transport. You will get 1 upon dm upon dt into Cp. Now coming to the first problem, I just request you all to start solve problem with me, and if you have any doubt, you can stop me and you can ask the question. So let us see the first problem. Clear any doubt, anything you want to ask? Okay. So let us begin to solve the first problem. So this assignment is also easier one. Just use the expression. There are so many expression in this current assignment. Whatever the formula is given in the textbook or in the lecture, you have to use, and just you will get the answer. So first problem is that a specification of a thermoelectric Peltier module from data sheet shown here. A 20-volt battery is connected to this electric Peltier module via series resistor RS, as shown in the figure below. What is the theoretical value of resistance RS such that it will satisfy all the parameters ratings of the given specification? So this is the Peltier module. So let us denote the voltage across Peltier module is Vp, and the current that is drawn by this Peltier module is Ip. So we are having, we can write the equation. So 20 minus Ip Rs minus Vp equal to 0. So this will give you, so here in this problem they are asking about the series value of resistance such that it will satisfy the parameter rating of the specification. So Rs will be 20 minus Vp upon Ip. So here the two temperatures given, one for 25 degrees Celsius and one for 50 degrees Celsius. So as it has not been specified, so let us find for both the cases and then we will select the answer. So first we will take the hot side temperature as 50 degrees Celsius, and here we take it as 25 degrees Celsius. So in 25 degrees Celsius, this Vp is given as 14.4 and Ip is given 6.4. So 20 minus 14.4 upon 6.4. So this Rs will come as 0.875. Now for 50 degrees Celsius, this will come as 20 minus 16.4 upon 6.4. This will come as 0.5625 ohm. Now tell which value should I select such that this will satisfy all parameter of the given specification. So we will select this higher value. So RS is taken as 0.875 ohm. Yes, 0.875. Why if we have selected Rajnikant? Can you tell the answer? Why we have not selected 0.5625?
Because because the range, the 0.875 will cover the range of the even 0.5625 also, sir.
Yes, correct. Like suppose if you have taken this value, suppose you have taken this 0.5625. So then if you take IP for 25 degrees Celsius, then it will come as 20 minus 14.44, and we have selected 0.5625. 20 minus 14.44 divided by 0.5625. So if you see this IP is coming as how much? 9.95 ampere. So this will not satisfy our uh, this data sheet. So this violates this Imax. So this is greater than Imax. So we have to take the higher value of resistance. So this violates the current rating of Peltier device. This violates the current rating of Peltier device. Therefore, we have selected RS is equal to 0.875 ohm as the answer. Right. So coming
Yes,
to
sir.
the next, yes. Okay, very good, Rajnikant. You have to understand before everything means how we have selected this one. It is not that a reason that it is higher value, then we have selected. It has some reason behind it. So let us come to the second problem. So in the second problem, what is the minimum temperature of cold side when hot side temperature is 25 degrees Celsius? Very easier one. So you have to see the data sheet only, and it is hot side temperature is given as 25 degrees Celsius. I am just writing the answer for previous one. So this answer is 0.875. So T for the next question, TH is equal to 25 degrees Celsius, and we have to find the minimum temperature at cold side. Since delta T max is given, delta T max is given for 25 degrees Celsius, our temperature is 66 degrees Celsius. So we know that delta T equal to Th minus Tc, and therefore Tc equal to Th minus delta T. Therefore, this Tc minimum will be, this is constant, Th is constant, so therefore this delta T max we have to take. So this is constant value. So Tc minimum will be Th is constant 25 degrees Celsius, delta T max is 66 degrees Celsius. So cold temperature will be minus 41 degrees Celsius. So this is the correct answer. Tc minimally minus 41 degrees Celsius. Now coming to the next problem. So for the specification of Peltier cooler shown below, what is the maximum coefficient when hot side of Peltier cooler is having temperature of 27 degrees Celsius? When hot side of Peltier cooler. So hot side is given as 27 degrees Celsius and operating at maximum current and voltage. So this operation range is given. It is operating as maximum temperature and voltage. So I max is 15 ampere and V max is 15.4 volt. So you have to find the maximum coefficient. So what is QC max from the data sheet? So from the data sheet, QC max for 27 degrees Celsius is given as 130 watt. From data sheet, we get heat energy extracted from the body is QC max is given as TH is for TH 27 degrees Celsius as 130 watt. And we know that COP is heat energy extracted upon electrical energy be provided. So COP of Peltier module, we know Peltier color we know by this expression. Here they are asking about COP max. So COP max will be QC max upon electrical energy input. So QC max is 130 and electrical energy input we can find from this V max into I max. So V max is 15.4, I max is 15. So electrical energy input is 231 watt. Therefore, we will get answer as 0.563. Mohan, you have not understand why we chosen high resistance. So I have told you the answer. Means if you have chosen the lesser value, then it will violates for this temperature 25 degrees Celsius. Now if you have chosen for 0.5625 ohm, then if you find the current flow for this Peltier device, then it will coming as 20 minus 14.44 14.4 upon this RP, that is 0.56, that is RS, 0.5625. So if you calculate, you get 9.95, while this I max is given as, this I max is given as, this I max is given as 6.4 only. So you cannot allow this amount of current flow through your Peltier module. It will blow up. So in order to save your Peltier module, you have to select that resistance that will cover all the range, not only a certain temperature value, certain hot temperature value. Right? What is the older question? What do you mean by older question? Okay, okay. Okay, no problem. Okay, so let us come to this problem 4, which are the flow true. So the first statement is, as the temperature difference between hot and cold side of Peltier cooler increases, voltage across the cooler decreases under the given condition of constant current. So I have given this thermal and electrical graph for this Peltier module. So from there you can also see. The first one is telling that as the temperature difference between hot and cold side pattern increases, and here they are showing a voltage. So we will see the electrical graph. So we can see this as we as the difference delta T. So this is delta T. As the temperature difference between hot and cold side increases, we go this side, voltage across cooler decreases. No, we can see that voltage across cooler is increases. So we can see this increment for a certain, for a given condition of current. So we can see this is so starting from here, this value is going to increase. So this one is wrong. Now coming to this next part, next option. The temperature difference between hot and cold side particular increases, removal of heat from cold side decreases. So again, we will go this side, delta T, removal of heat from cold side decreases. Yes, we can see this as the delta T increases, removal from heat from cold side decreases. So starting from 8, suppose for this 0.6 ampere current, starting from 8, it is going down. So this is the starting value, it is going down. So this is a starting value for 3 ampere current. So this is going down if you increase the delta T. So second option is correct. Coefficient of performance can never be greater than 1. This is incorrect, as we have seen just this COP max. Sorry, here it's coming as less than 1, but it is greater than 1. More the COP, it is better one. The current for this Peltier cooler is allowed to exceed the current. No, you cannot violate the data sheet. Otherwise, it will blow up. So the current is not allowed to exceed the current. So correct answer is B. Now coming to the next problem. So here an, an aluminum heat sink in the figure shown below has a temperature of 50 degrees Celsius on higher area surface. So one side we having 50 degrees Celsius, and another side, opposite side, we are having 50.1 degrees Celsius. What is the power dissipation of heat sink in watts, whose dimension is given as 40 mm cross 40 mm cross 3.5 mm? Consider thermal conductivity of aluminum as 211 watt per degree Kelvin per meter. So this is problem from this heat transfer by conduction. So this heat conduction expression we can see Q equal to K into A delta T upon delta X. So we will use this expression. So we have expression. First write the thermal conductivity. Thermal conductivity is given K equal to 211 watt per degree Kelvin per meter. And let us find the area through which this heat flow happens. So area will be 40 cross 40 to 10 to the power minus 6 meter square, and delta is x is the width of the heat sink. So width of heat sinks will be 3.5 into 10 to the power minus 3 meter. Now you will use this heat transfer equation, power dissipation of the heat sink. So Q equal to Ka into delta T upon delta X. So all value we have known. So A is 211, delta T is 0.1 degree Celsius. So in Kelvin also it will be 0.1 degree Kelvin, and area is 160 into 10 to the power minus 6 meter square upon delta X will be 3.5 into 10 to the power minus 3 meter. So this Q will come as 9.65 watt. So the 9.65 watt is the correct answer. Yes, Rajnikant, correct. Very good. So let us see the next problem. For the data given in question 5, what is thermal resistance in degree Celsius per watt of heat sink? So we know the for conduction problem, this heat dissipation expression is Ka into delta T upon delta X. For conduction, and general expression we know that P equal to delta T upon R theta. That is thermal resistance. So comparing both these, compare both equations. Compare both equation, you get R theta as delta x upon Ka. So delta x is 3.5 into 10 to the power minus 3 meter, and K is thermal conductivity. So thermal conductivity is watt per degree Kelvin per meter, and this area is 160 into 10 to the power minus 6 meter square. So just to verify whether we can thermal conductivity write in per degree Kelvin or per degree Celsius are same or not. I think both are same. So you can also write per degree Celsius. So if you equate this equation, then it will come as 0.01036 per degree Celsius, degree Celsius per watt. This is the answer. 3.5 upon 211. Here I have made mistake. It is 1600. So it will be 1600, and so here will be also 1600. Then you will get answer as 0.01036 degree Celsius per watt. Yes, 0.001. Correct, Rajnikant. Very good. Now coming to the next problem. Problem number 7. An aluminum heat sink is used for forced convection cooling as shown in the figure below. What is the Reynolds number for forced convection cooling if velocity of forced air is 10 meter per second? Refer Big 9 lectures for empirical formula. Kinematic viscosity of air is 1.8. So here, sorry, one mistake there. 1.8. Into 10 to the power 5 minus 5. meter square second. So let us first see the expression for this heat sink for post convection. So let us come to this expression first. So this one is the expression for Reynolds number, R equal to Ux upon mu. So just write the equation first. So all of you just use this expression, this convention expression, and get the answer. So so this R value, Reynolds number, we have to find what are the value given. U, mean velocity of forced fluid air, is given as 10 meter per second. And this mu value they have provided as kinematic viscosity of air is provided as, this one is mu 1.8 into 10 to the power minus 5 meter square per second. Therefore, this Reynolds number will be Ux upon V. So how, what will the X characteristic dimension? So this characteristic dimension for this rectangular plate will be only this length only. So X will be characteristic dimension for this plate will be length of the heat sink, that is 40 mm. Now we will put all this value 10 meter per second and X is 40 mm and this kinetic velocity of air is given as mu is given as 1.8 into 10 to the power minus 5 meter square per second. So this will provide you 22 point equal to into 10 to the power 3 is the correct answer. Yes, Rajnikant, very good. Let us come to the next problem. Question number 8. So the heat sink discussed in problem number 7 has been used for forced convection cooling. Post convection cooling. Calculate the power dissipation in air if temperature of heat sink is 70 degrees Celsius and the ambient temperature of air surrounding the heat sink is, yes. Consider expression for Nusselt number is as n equal to 0.664 into R R to the power 0.5 into V upon del to the power 0.033 for laminar flow. That is for Rayleigh number below 5 lakh, and for this Nusselt number for turbulent flow, that is for Rayleigh number greater than 5 lakhs, that is 0.37 into R to the power 0.8 into V upon del upon 0.33, where mu is the spanoptic viscosity of air as 1.8 into 10 to the power minus 5 meter square per second. Daily thermal diffusivity of air as 2.6 into 10 to the power 5 meter square per second, and R is the Reynolds number, which is equal to the value computed in question 7. Dimension of heat sink is given as 40 mm, 40 mm cross 3.5 mm. Thermal conductivity of air is 0.026 watt per degree Kelvin per meter. So in this question, what they are asking? They are asking about the power dissipation in air. So the power dissipation happens from the top side also and from the side section also. So we have what are the things given here? So temperature at hot side is given as 70 degrees Celsius, and ambient temperature is given as 30 degrees Celsius. So temperature of heat sink is given 70 degrees Celsius and heat sink given 30 degrees Celsius. And Nusselt number is given, but first this Reynolds number R is given. Sorry, I am telling about the Rayleigh number, but this is Reynolds number. So Reynolds number we have got from the previous expression. So Reynolds number we got as so this is less than 5 lakh. Since the Reynolds number is less than 5 lakh, therefore we will use this expression, this first one, for finding the Nusselt number 0.664 into R to the power minus R to the power 0.5 into V upon del upon 0.33. So this is the expression that we got from the Reynolds number after finding the Reynolds number. So this velocity of kinematic viscosity of air is given as 1.8 into 10 to the power minus 5 meter square per second, and thermal diffusivity of air is given as 0.26 into 10 to the power minus 5 meter square per second. So these are things given. Now coming to the next page. So and dimension of heat sink is also given. Dimension of heat sink is given as 40 mm cross 40 mm 3.5 mm, and this K value thermal conductivity is given as 0.026 watt per degree Kelvin per meter. So the dimension of heat sink you can make like this. So this is 40 mm. And this height is 3.5 mm. So power dissipation formula we have to write for convection. Power dissipation formula is Q equal to A Nusselt's number and then delta T upon F. So first we find the Nusselt's number. The Nusselt number is 0.664 into Reynolds number upon 0.5 and then kinetic viscosity of air and this del 0.33. So if you put the values, all the values 0.664, Reynolds number is 2 10 to the power 3 upon 0.5 and mu is 1.8 into 10 power minus 5 and del is 2.6 into 10 power minus 5.33. So we will get 87.67. That is both for Nusselt number same for side and for top because it depends upon the Reynolds number. So Reynolds number will not vary. So both this Nusselt number for side or top both will be same for both aspect. Now this delta T is 70 minus 30. That will give 40 degrees Celsius. And this X is given as 40 mm. And then we will find this area of side and area of top. Side area will be this 40. This one is the side area. So this is the side area. So this is the side area. Side area will be 40 into 3.5 into 10 to the power minus 6 meter square. And top area will be 40 into 40 10 to the power minus 6 meter square. Therefore, the power dissipation, heat power dissipation will be Q top on Q side. So only this will vary. Area, other will be remain same. So we will write it as A into N into delta T upon X into areas side plus area top. And if you see this side area, then there are 4 sides. So we have to multiply it with 4. So we will write it as K value is 0.026, and then Reynolds, then Nusselt's number is 87.67, and delta T is 40, and this characteristic dimension is 40 mm, and area of side will be 40 into 3.5 10 to the power minus 6. And one important thing is here that you have to multiply by 4 because there are 4 sides. Plus top area will be 40 into 40 10 to the power minus 6. So if you do simplification, you will get 4.923 watt. So the correct answer is 4.923 watt. Yes. So this is a little bit lengthy problem, but here all things are given. You will first find the Nusselt's number. Nusselt numbers we got from Reynolds number, and then after finding the Nusselt's number, we have to this power dissipation formula for convention. Here this Nusselt numbers come. So Nusselt number k into a into n into delta T upon x. So then you have to see this convention from the top and from side also. From side, you have to, there are 4 sides, so you have to take care of all the 4 sides. And this convention will happen from top side only because bottom side, the element will be present. So from the bottom side, we have to not consider. So you have to consider only top side. That's why we have not multiplied with 2. So you will got this power dissipation as 4.923 watt. Now coming to the next problem. So which of the following has lowest thermal conductivity? So among these 4, you have to find the lowest thermal conductivity. Yes. Problem 9. Glass, steel, copper, air. Yes, Ramesh, very good. Air having the lowest thermal conductivity. And which how the following has highest thermal conductivity? Glass, steel, copper, air. Copper. Yes, Rajnikant, very good. Copper has even highest thermal conductivity. So you can correlate with the material characteristics, and you can also go with the data. If you see the data, I think sir has mentioned at one place. Yes, here. So let us copy it. Then we can see from here also thermal conductivity, which is having higher. So glass has thermal conductivity of 1.05. A steel has thermal conductivity of 47.6. Copper has thermal conductivity of 385. Air has thermal conductivity of 0.026. So lowest thermal conductivity is having air and highest thermal conductivity having copper. And silver has even more thermal conductivity than copper. Now coming to the next problem. So here, as shown in the figure, a battery of 30 volt is interfaced by using an electronic converter with a Peltier module. Find the maximum duty cycle at which the switch can operate for the safe operation of the Peltier module at 50 degrees Celsius. Answer up to 3 decimal points. This is very easy problem. So this converter is buck converter. Whoever is getting answer, please type on the chat box. So input voltage is 30 volt. Since converter is buck, let us take this voltage across Peltier module is VPM. So V out equal to VPM is equal to 16.4 volt. How we got? We got from the data sheet 16.4 volt, and it is specified for 50 degrees Celsius. So 16.4 volt. So 16 point VPM equal to D into V in. So we will get duty as 16.4 upon 30. So 0.547 is the answer. Now coming to the next problem. The series resistance RAC is connected to the Peltier module as shown in the figure if a duty cycle of 0.7. So duty cycle is specified. So let us first find this V naught. So we are taking this. So here it is VC given. So VC will be D into V in. So DT ratio is 0.7. V in is 30. So 21 volt is the VC voltage. Now we are having this 21 volt and this series resistance is given. RAC and this VPM is we have to find, and IPM. So these problems from previous one. So we take it is for 50 degrees Celsius. So RAC will be 21 minus VPM upon IPM. So 21 minus VPM is 16.4. So this one is VPM and IPM is 6.4. So we will got 4.6 upon 6.4. So it will be 0.72 as the answer. Now coming to the next problem. The emittance of polished aluminum so again question 11. Yes, Ramesh, anything you want to ask here? Okay, so let us come to the 13th problem. The emittance of polished aluminum is. So the polished aluminum and options are given here, and it is multiple select question. So this question is multiple select question. So aluminum polished air is emittance is given as 0.095. So you have to compare with other one. So first one is given as less than anodized aluminum. Anodized aluminum is 0.8. So it is less than it. So it is correct. More than rough surface aluminum. Rough surface aluminum 0.18. So its value is 0.8. So it is correct, but its value is 0.18. So it will incorrect. Less than wood. Yes. Wood value is given as 0.9, but its value is 0.0095. So it is correct. More than polished air. Polished air, more than polished copper. Polished copper value is 0.07. So D and C both are correct. Less than wood, yes, it is less than wood. More than polished copper, it is more than polished copper. Now coming to the next problem. In a convective Peltier cooling system, in a convective Peltier cooling system, an air blower is used over the hot surface of the square-shaped Peltier element with a side length of 4.5 centimeter. If Reynolds number is 2500, then find the air speed in meter per second coming from the blower. So we have to use the expression for post cooling system. So we have seen the expression, Reynolds number expression we have seen is mu x upon kinetic viscosity mu, sorry, u x upon mu. So Reynolds number is u x upon mu. So this is for forced convection system. So this Reynolds number is given as 7500 and air speed is given as air speed you have to find, and the side length is 4.5 centimeter. So this will be characteristic dimension 10 to the power minus 2, and then kinetic viscosity is given as 1.8 into 10 to the power minus 5 meter square per second. So if you simplify it, you will get U as 3 meter per second. So from here, you will get U as 13500 10 to the power minus 3 upon 4.5. So correct answer is B. So let us see next problem. A solid slab. So this problem is from the conduction heat dissipation. A solid slab shown in the figure has dimension as follows. Length is 5 centimeter, width is 1.5 centimeter, height is 3.5 centimeter. Cold side temperature as 293 Kelvin, and hot side temperature is 307 Kelvin. For a difference between the Q1 and Q2 of 25 watt, calculate the thermal conductivity of the slab. So we know the thermal dissipation for conduction is K into A into delta T upon delta X. So we have to find the thermal conductivity. That means we have to find the K value. And the difference of Q1 and Q2 is given as 25 watt. So 25 is given, K we have to find, and area we got from length and width. So area will be 5 into 1.5 into 10 to the power minus 4. And how much delta T? Delta T 307 minus 293. So 307 minus 293 will be delta T. And then delta X will be this height. Sorry, I have taken wrong. This height will be taken as this area and this width is 1.5. So this will be taken as delta X along which this heat transfer happens. So this one is 3 point, this one is 5 centimeter, length is 5 centimeter, and height is 3.5 centimeter. So delta X will be 1.5 into 10 to the power minus 2. So if you do it, then you will get thermal conductivity value as 15.306. So approximately equal to 15.3 watt per degree Kelvin per meter. So the answer is 15.3 watt per degree Kelvin per meter. Because if you see the expression for this heat transfer through conduction expression, like I am showing you. So see here, heat transfer by conduction. So this area is the that amount of area through which this heat transfer happens, and delta E is the thickness of block along the heat flow direction. So we have to go through this expression. I hope by seeing this slide you are able to understand. For area, you have to consider surface area, not this volume. Whatever you are taking Mohan Chidambaram, this that is volume, not the area. So we have to consider the surface area, and surface area is this one, the contact surface. The contact surface is this length into height, while the width is that it has to this cross this area for the heat transfer. And surface area, then we have to consider this length into height. Come on. So let us see the next problem. What is the maximum amount of heat in kilowatt that a 2-meter thick anodized aluminum block radiator measuring 10 meter in length and initially 80 degrees Celsius can dissipate from top side system through radiative transfer of meter 40 degrees Celsius? So this problem is from the radiation, right? So this problem is from the radiation. And for the radiation, we have to use the expression that has discussed. You can use some other expression also, but whatever has been discussed in the class, we are going to use that equation. So this problem is from the radiation part. So the heat dissipation through radiation, we know that HR into A into delta T. where this HR is radiation thermal coefficient, radiation thermal coefficient, and area is area of surface, area of surface perpendicular to radiation direction. Perpendicular to radiation direction. And how will you find this HR? HR, for finding the HR, for finding the HR, the expression is 4 sigma epsilon 1 minus phi T1 plus T2 upon 2 to the power 3. So this is the HR, radiation thermal coefficient. So let us first find the HR, and this is Boltzmann constant. Boltzmann constant. And Boltzmann constant is 5.67 to 10 to the power minus 8. So let us find the HR first. So 4 into 5.67 into 10 to the power minus 8. Epsilon is emissivity. So emittance of the anodized aluminum is 0.8. So epsilon is 0.8. And since this is single or parallel system, single or parallel plate, so phi will be 0. So it will be 1 minus 0. And T1 is 273 plus 80, and T2 is 273 plus 40 upon 2 to the power q. So we will get 4 into 5.67 to 10 to the power minus 8 into 0.8 into 333 q. So you will get 6.7. Therefore, the maximum amount of heat that will transfer through radiation will be 6.7 into area will be, area is 2 meter thick and 10 meter length. So 2 into 10, and delta T will be 40. So you will get 5.3 5359 watt. So it is approximately equal to 5.36 kilowatt, right? 800 into 6.7. So answer for this problem is 5.36 kilowatt. Now coming to the next problem. So here we are using this shielding factor because two surfaces are in contact. So let us, how we will find, since there are two surfaces, so it will be QC plus, so heat dissipation through copper plus heat dissipation through aluminum. So both we will add up. So for first we'll find the QCU. So QCU will be HR into area. For copper, what is the area? So for copper, area is 2 meter height and 5 meter is the length. So 5 into 10, 5 into 2 meter square, and delta T will be, delta T is same for both. So 80 degree minus 30 degree, that is 50 degree Celsius. So this is the area. Now we have to find HR for CU. HR for CU. So HR CU A into delta T. So HR CU area is 10 and delta T is 50. So HR CU radiation thermal coefficient will be 4 into sigma epsilon 1 minus phi T1 plus T2 upon 2Q. So here sigma both epsilon is different for both. So epsilon is different for both. So impedance for aluminum is 0.095 while copper is 0.07. So this is we consider for epsilon. 4 into 5.67 into 10 to the power minus 8. Epsilon value is impedance value is 0.07 and shielding factor is 0.8. So into T1 plus T2. So T1 is 273 plus 80 plus 273 plus 30 upon 2. So if you do say calculation, you will get it as 0.112. Therefore, we will get heat radiation. Heat radiation from copper will be 0.112 into 10 into 50. So you will get it as 56 watt. They will give HR or I have to calculate. Most in safe zone you can remember. I am not confirmed about this part, but in safe zone you have to remember because this expression has been given by discussed in the class. Anyway, these sorry. Like if you see this radiation expression, this one Q equal to HR into A delta T, where this HR expression is this one. So if you more practice the problem, you will easily memorize the expression. In safe zone, you can remember the expression, but I am not confirmed that they will provide it or not. One thing I am sure that they will ask problems similar like the assignment or that has been discussed in the this problem solving session. But what the part they will give or not, I'm not clearly saying. So let us see the for Q aluminum. So this for Q aluminum heat radiation through aluminum polished aluminum will be so HR aluminum and area will be different now. Area will be 10 to 2 that is 20 meter square and delta T will be same. And HR aluminum will be 4 into sigma epsilon aluminum 1 minus phi T1 plus T2 upon 2. So 4 into 5.67 into 10 to the power minus 8. Epsilon value is 0.095 and 1 minus 0.8. So you can write 0.2. So this will be same T1 plus T2 328 Q. So this will give us point 0.152. 0.152. Therefore, you will get Q aluminum as 0.152 into 20 into 50. So you will get 152 watt. So total rate of heat, radiative heat transfer will be Q equal to, so therefore Q will be 56 plus 152. So you will get 208 watt. Now coming to the next problem. So this is from mass transfer. Mass transfer equation we will know QH is equal to dm upon dt into Cp into delta T. So it is asking in this problem, they are asking about thermal resistance. Thermal resistance for mass flow rate. So again, we will compare this equation with delta T upon R theta. So if we compare both equation, then you will get R theta m as 1 upon dm upon dt into Cp. And this dm upon dt is given as 10 gram per second and Cp is given as 184 joule per gram per Kelvin. So if you do the simplification, you get as 0.0024 Kelvin per watt. So joule per second will give you watt. So this is the answer. Now come to the next problem. So this is the problem from this thermal visualization. So we know this. We can directly write from this Tc minus Ta equal to R equivalent into this Qc. So Tc is given as 80. So this value is given as 80 and Ta is given as 30 and ambient temperature is 30. R equivalent is RCH plus RHS plus RSA and this QC is 50 watt. So 50 upon 15 equal to 0.75 plus 0.5 plus RSA. So this RSA will come as 3.33 minus 0.75. It is 2.08 degrees Celsius per watt. So 2.08 is the answer. Now coming to the next part. So this is very simple. The energy stated on the cold junction is 25 watt and the electrical energy supplied is 20 watt. So what is the heat transferred to the hot junction? So PH is equal to QC plus E. So it will be 45 watt. So anyone having doubt? So today we have done with the current assignment. Anyone want to ask something? Which is shielding factor 0 in question 16. Yes. Yes, we have to shielding factor 0 because it's a single single system. It is not connected with any other material, uh, substance. Single system or parallel system, you have to consider shielding factor 0. If it is connected to another substance, then the shielding factor is given. So we have 6 attendance, 5 attendance is there. Ramesh, Prabhakaran, Mohan Chidambaram, Rajnikant, Mayor Kegar. For single side, pi equal to 0. What is pi? Shielding factor? Yes. Shielding factor for this, sir has discussed it. Like here, for single or parallel plate system, it is 0. While this shielding factor is given for this system wherever these two surfaces are in contact, then the shielding factor given, and you have to just manipulate the equation. Any other doubt? Okay, thank you everyone for attending to this session, and we will meet on the next Sunday at the same time. And a good night to everyone. Thank you all.